Hi, this is Paul from All About Digital. This is Chapter 3, Part 1 of a three-part series on Karnaugh maps. In this section of Chapter 3, we're going to talk about truth tables and how they're represented and how they'll eventually transition to a Karnaugh map. So please like the video, subscribe, and list any comments down in the comments section. I hope you enjoy the video. Thanks for watching. This is Chapter 3, Part 1, Karnaugh maps. In this video, we're going to learn what a truth table is and how it's used. We're going to learn about standard product and standard sum forms when describing Boolean expressions. We're going to learn about min-term and max-term representations of Boolean expressions and how and why they're used. And we're going to learn how to use Karnaugh maps to reduce and optimize Boolean expressions. First, let's do some definitions. The first definition is the definition of a literal. A literal is the occurrence of a variable in either its complemented or uncomplemented state. The product term A, B, C bar has three literals, A, B, and C bar. Here's another product term, X, Y, Z, W bar. This term has four literals, X, Y, Z, and W bar. Okay? The next definition is a product term. A product term consists solely of the product of literals. In other words, every literal in this term is multiplied together and forms a product term. So this is a product term right here because they're all multiplied together, A, B, C bar. A, B plus C bar is not a product term because of the plus operator right here. This is not a product term. Okay? The next definition is a sum term. A sum term consists solely of literals in a sum term. For instance, A plus B plus C bar is a sum term because each of the individual literals are summed together. The term A times B plus C bar is not a sum term because the multiplication operator is a multiplication term and not a sum term. They all have to be summed together to be a sum term. The domain of a function is a set of variables for which that function exists. For example, function of x, y, z implies that a function exists for variables x, y, and z. If you had a function of a, b, c, for instance, f of a, b, c, the only literals that can occur in that function are a, b, and c in either their true or complemented form. A standard product term is a product term whose variables all appear once and only once in either its true or complemented form. So what do we mean by that? If we have a function whose domain is a, b, and c, a standard product term, which is this one right here, contains all of these literals, a, b bar, c. If it only contained a, b bar, it would only be a sum term. But if it contains all of the literals, it's a standard product term. And as another example, function of abc equals a bar b is not a standard product term because it's missing the literal c. A standard sum term is a sum term whose variables all appear once and only once in either its true or complemented form. Thus, function of abc equals a plus b plus c bar. This is a sum term, and it's a standard sum term because all the literals a, b, and c appear in that sum term, a, b plus c bar. Alternatively, if you have a sum term f of abc equals a plus b bar, this would not be a standard sum term because it's missing the variable c. There's two forms, and we're going to talk about the first form. The first form is called the sum of products form. And an expression is in the sum of products form if the expression is a sum of product terms. For instance, in this example, function of ABC equals AB bar, that's a product term, plus ABC, a product term, plus AB bar C. This is in the sum of products form because each term is a product term and you're adding those terms together. So it's a sum of products form. Okay. The next definition is the standard SOP form. An expression is in the standard SOP form if each term is a sum of a standard product term. For example, the expression f of ABC equals a b bar c. Well, that's a standard product term because it contains all the variables, all the literals a, b, and c. The second term, a bar b c bar, contains all the literals a, b, and c. So that's a standard product term. And the last term, a b bar c, is also a standard product term because it contains a, b bar c. So if all the terms are standard product terms, this one, and this one, which they are, this is in the standard SOP form. So this is the standard SOP form, again, because all the terms are standard product terms. And alternatively, for the product of sums form, an expression is in the product of sums form if it is the product of some terms. For example, the expression function of ABC equals, first term is a plus b plus c, and that is a sum term, okay, a plus b plus c, term 1 multiplied by another sum term, a plus b bar. So if each of the terms are sum terms and they're all multiplied together, it is in the product of sums form. Okay, the standard product of sum forms just states that it's a product of sums form, but every sum term in this product is a standard sum term. That means that each term contains all three literals, for instance, ABC in this function. A plus B bar plus C. Okay, that's a standard sum term. Term 2 contains A bar plus B plus C bar. That's a standard sum term. Term 3 contains A bar, B bar, C bar. Again, that's a standard sum term because they have, again, literals A, B, and C within the term. This is called a standard product of sums form, or POS form, because terms 1, 2, and 3 are standard sum terms. Okay, a truth table provides a tabular representation of a function, and it lists the output values of the function for all possible input combinations. For example, in this particular example, the function is equal to a plus b plus c, which means that the function is going to be a 1 when either a is a 1, b is a 1, or c is a 1. Okay, we can show this in a tabular form, which is called a truth table, and we identify the 8 rows in the truth table, 0 through 7. Then we show the variables, or the literals, a, b, c, in binary from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7. So this function defines for inputs a, b, and c what the output is going to be, and that's f. For instance, when a is 0, b is 0, and c is 0, f is a 0, because let's look at this function right here. The function is only a 1 when either a is 1, or b is 1, or c is 1. Okay, let's look at the second term. Well, in this one here, we have c is 1, so the function's a 1. This one here, we have b is 1, right here. So we have a 1. The third one, we have b and c are 1. So b and c are both 1, so we have a 1. This one here, we have a is a 1. And a is a 1 all the way down to 7. from 4 to 7. So there's a 1, 1, 1. So this truth table right here represents this function right here in a tabular form that shows for these particular inputs, this is what the output of the function is going to look like. So you can draw a particular function like this. Oop. And you have 3 inputs. Let's get down here again. You got A, B, and C, and this is the function out here. And inside here you have the logic. So this function states that you have 3 inputs, variables A, B, and C, and you have 1 output F. And the logic that you designed, this Boolean expression right here, is implemented in logic, some sort of logic, which we'll talk about, that will create this output F whenever you get the right combinations of the inputs A, B, and C. Okay? Another example. Here's another function that equals AB plus BC. Okay? Let's analyze this one. This function is going to be a 1 whenever A and B are both 1. We don't care about what C is in this instance. Or when B and C are both 1, and we don't care about A in that instance. So let's do the AB first. So let's look at whenever A and B are both 1, the function is going to be equal to a 1. Where is A and B both 1? A and B are both 1 right here and right here. Okay? So A and B are both 1, and we don't care about C because we're just doing the first one here, AB. The output is a 1. Okay, how about this one here? It says whenever B and C is a 1, we don't care about what A is for this term. The output is a 1, okay? B and C, well, 0, 0, 1, 1, 0. B and C is a 1, so the output's a 1. Okay, if we go down here, also B and C is a 1 here too, but it's already covered by the AB. So this is the BC portion covered, and this is the AB that defines this function. And again, we have the function F, and then this is the expression that's going to be implemented, AB plus BC, and we have 3 inputs, A, B, C. And this is the logic that we're going to implement right here. Okay, now we're going to define some new terms here that actually, when we get into Karnaugh mapping, that kind of help us minimize the representation of certain functions. They're called min terms and max terms. What do we mean by that? Well, min term is a description of the product terms for each particular row in a truth table. And in this case, we have 3 variables, so we have 8 combinations. So in row 0, the min term little m0 is equal to A bar, B bar, C bar. Now it's A bar, B bar, C bar because A is a 0, B is a 0, and C is a 0. So M0 right here is equal to A bar, B bar, 0. Again, if A is a 0, it's A bar, B is a 0, it's B bar, and C is a 0, it's C bar. So the standard product term, or the min term, M sub 0 for the 0th row, is A bar, B bar, C bar. Okay, let's go to the first row. First row, we've got M1 lines up with row 1, and what is the value of A, B, and C in row 1? A is a 0, B is a 0, and C is a 1. So the min term associated with row 1, we make it a bar, we complement it if it's a 0, and we don't complement it if it's not a 0. So we got 0, 0, 1, so we have A bar, B bar, C. So M1 is A bar, B bar, C. Okay, let's go to the next row. Row 2, M2, min term 2, row 2. What is the product term in row 2? Row 2, we have a 0, 1, 0 for the input combination ABC. So the minterm is, since A is a 0, we have A bar, B is a 1, we have B, and C bar. Since C is a 0, we have A bar, B, C. That's M2. Let's do M3. Okay, see how easy this is? All right, row 3, we have 0, 1, 1 for minterm, little m3. So A is a 0, so A bar, and then we have BC. So M3 is A bar, BC. M4 is 1, 0, 0, so we have A, B bar, C bar, because B and C are both 0. That's M4. M5, we have A, B bar, C, because we have 1, 0, 1, A, B bar, C, that's equal to M5. Little m6, A, B, and C are 1, 1, 0, so we have A, B, C bar, because C is a 0. That's M6. M7, right here, all the variables are 1, so we have A, B, C equals M7. Okay? Let's look at the max terms. The max terms, as we're going to find out, this minterms define in a functional truth table the ones of the function, and don't worry about that right now. The minterms define the zeros of the function, okay? Because if you look at this truth table back here, it's got zeros and ones. So yes, the minterms define where they're going to be defining where you have the ones in your function, and the max terms will be where you have the zeros in the function. But we're going to get into that in more detail. Okay, but let's look how we form the max terms, and the max terms happen to be standard sum terms, okay? So for row 0, big M, signify a max term with a big M, max term 0 is equal to A plus B plus C. So it's just the opposite of the minterms. Whenever the literal or variable is 0, you represent it with the uncomplemented form for that variable. In other words, A is a 0 here, you make A non-complemented. So M0 is equal to A plus B plus C equals A plus B plus C. Okay, that's an A. All right, so we'll go down the line here. M1, this is a standard sum term. We'll go down the line here, and row number 1, this is big max term 1 here. We have A plus B plus C bar. Well, that means that A is a 0 and B is a 0 and C is a 1. It's just the opposite. So when C is a 1, we have a C bar, and vice versa. So M2, we have 0, 1, 0. So a 0 means it's a true form. 1 means it's complemented. So we have a B bar, and 0 again means it's a true form. A plus B bar plus C. Okay, let's look at 3. That's 0, 1, 1. So 0 means it's uncomplemented. 1 means it's complemented for B, B bar, and C bar. Let's look at 4. We have 1, 0, 0. So the 1 means A is complemented. So we got A bar plus B plus C for 0, 0. And 5, we've got 1, 0, 1. So the 1 means it's complemented. 0 means it's not. And 1 means it's complemented. So we have A bar plus B plus C bar. Standard sum term for row 5 or max term 5. Okay, max term 6 is 1, 1, 0. So A bar, B bar for 1 and 1, and then 0 is uncomplimented. And then the 7, of course, is all ones, so it's A bar plus B bar plus C bar, and that's max term 7. Okay, makes sense? Hopefully. So, again, a minterm, M sub I, is a standard product term. The subscript I, right here, is the row number of that particular minterm in the truth table. So let's look at this function right here. We're going to define where the function is a 1. Okay. It's a 1 here, it's a 1 here, it's a 1 here, it's a 1 here, and it's a 1 here. And we can write it as the sum of wherever the minterms are a 1. Well, the minterms right here, this is M1. Okay, so it can be the sum, this is the standard product term, it can be the sum of minterm 1 right here, which is A bar B bar C, plus M4 right here, which is A, B bar, C bar. So we don't have to write A bar, B bar, C bar. We can just write M4. And then we have M5. That's standard product term A, B bar, C right here, plus M6. Oh, there's M6 right here. Okay, M6, which is A, B, C bar, and then we have M7, which is ABC for the standard product term. Now, we don't even have to write all these like that. We can just say, we can use the standard function of ABC. This is the summation sign here. The summation, which is the sum of products of these standard product terms. 1, 4, 5, 6, 7. So function of ABC. I'll write that out again. Equals the summation of, well, there's 1, row 1, product term. Row 4, product term. And then row 5, product term. And then row 6, product term. And then row 7, product term. Okay, which is exactly the same as that. Okay, so that's how you can represent a truth table, okay, with its standard product terms. And this is just kind of a shortcut, and it's called a minterm. And the minterm is a standard product term associated with each row in the truth table. Again, this is the truth table. These are the input combinations, and this is the output function. Okay? Now the max term. Well, as we discussed previously, the max term defines the product of some terms for the zeros of the function. So they're true whenever there's a 0 in the function. Well, we have a 0 at row 0, we have a 0 at row 2, we have a 0 at row 3, and that's it. So we have 0, 2, 3. So we know that it's going to be the product of these 3 sum terms to define the zeros of the function. So row 0 is max term A plus B plus C. So that's M0 right here, M0. That's sum term times M2, which is the standard sum term. We're multiplying these together because this is the product of sum terms. So sum term M0 times sum term M2 times sum term M3. So this is the product of sums form when we're using max terms defining the zeros of the function. So a more convenient notation is just this multiplication sign right here. And the shorthand would be, this is the multiplication of standard sum terms 0, 2, and 3. 0, 2, and 3. And again, that's where the function is equal to a 0. So you can define a function in a truth table either by the ones of the function, where the function is a 1, or when the function is a 0, because the output of this function is either going to be a 0 or 1. So you can design your system using the zeros of the function, or you can design it using the ones of the function. If you're going to use the ones, you're going to use the minterm representations, and it's going to be the sum of standard product terms. If you're going to define it using your zeros, it's going to be product terms, max terms, and there's three of them in this case, 0, 2, and 3. It's everything that's not a 1. And this is it's the product of standard sum terms, 0, 2, and 3. Okay? So as you can see, function of ABC in the midterm representation, this is the ones of the function right here, 0, 2, 3, 5. That same function is equal to f of ABC, the max term representation, which is the product of the standard sum terms, which is the 0 of the zeros. So the zeros are 1, 4, 6, and 7. So there's a 0, 1, 4, 6, and 7. Okay. And the ones are 0, 2, 3, 5. 0, 2, 3, 5. So we've completely defined the function, either using the sum of products form, ones, or using the product of sum forms, zeros. So as we'll see, we can define our circuits either using this form or using this form. Why would we want to use one or the other? Well, one might be simpler, and as we'll see, as we get into gates and other logic functions, there's two basic gates called universal gates, and the two universal gates are these right here. I don't want to get too far ahead here. This is called a NAND, and then the other universal gate is called a NOR. This is like the AB input, and this is the functional output. Okay, this is called a NOR, N-O-R. So these are two universal gates, and they're very easy to implement in the standard circuitry that we have nowadays, which is basically CMOS. Almost everything's CMOS nowadays. And we're going to talk about that too, what that is and how it's implemented. But these are the two universal gates. So if you only wanted to use NAND gates in your implementations, you would use the sum of products form, because everything just falls out, the two levels of logic in the sum of products form using NAND gates. If you wanted to use a product of sum forms or design to the zeros, you would use NOR gates. Everything you use would be a NOR gate. So you can choose which way you want to go, either a NAND or a NOR. Okay. In this video, we discussed the SOP and POS representation of functions within a truth table. Min terms and max terms were discussed with a description of how they relate to sum of products and product of sums forms. Well, that's the end of part 1. I hope you enjoyed the video. Please like, subscribe, and leave comments. And we'll see you next time for part 2. Thanks for watching.